All right, good morning. Welcome. How are you all? Right. Seem like you need to be a little more lively. Like my voice needs to be a little more lively, apparently. So this is kind of advanced topics in environmental engineering, but it's specifically water quality, meaning aquatic chemistry. So our course for this semester is going to be aquatic chemistry, essentially, going a little bit beyond basic fundamentals, really exploring essentially a lot of different aspects of how equilibrium chemistry interacts with other components of the environment that we care about. And so this is related to water treatment, but this is not a water treatment class. We're going to deal with some geochemistry, some redox chemistry, bit of gas exchange. So we're going to cover 4 kind of primary things that our syllabus that I'll show you in a couple minutes kind of deals with, and really kind of directing our study, trying to follow a couple different books, and I'll tell you a little bit more about that as well. Okay, so that's kind of the big picture. My name is Samuel Snow, as you probably know, and I'd also like to get to know you guys a little bit and give you an opportunity to hear from one another. So in just a moment, I'll have you kind of share a bit. But just briefly, I've been here at LSU for, I guess, 8 years now. So I just crossed the 10-year mark about a year ago, and I've been teaching. My expertise really is in water treatment technologies, a lot of disinfection, a lot of UV or solar activated systems, and some surface science in there as well. So I have not taught this particular course before, but it is kind of within my wheelhouse. So I'm looking forward to that. It'll take me some time getting everything developed and organized for the class. So ask your patience, and I'll also be patient with you, especially knowing that perhaps I'm not always going to teach to the level that I would like to help you understand the topics, right? So there's going to be a bit of a mutual exchange there I think will be needed. Okay, so with that, can I have each of you kind of say your name, what your major and kind of research interests are, and maybe how long you've been at LSU, and we'll start here.
Hi, my name is Dev, and I'm doing PhD in environmental engineering. My topic is microwave treatment of wastewater, and Dr. Mo is my supervisor.
Great.
And I started my PhD in fall 23.
Okay, thank you.
I'm Katie. I'm a third-year PhD student. I work with Dr. Mo. We study bacteria that break down pollutants in the environment.
Thank you.
My name is Michael. This is my 6th year at LSU, but my first as a grad student. I worked with Dr. Mo doing 2 different projects. One with microbes producing pollutants in the groundwater, and we're starting another one for amine-based carbon capture.
I'm Maddie. This is my first semester of master's. I work for Dr. Snow. And I've been doing research on this compound called hydroxylamine for about a year and a half. So it's actually starting as a grad student.
Yeah, thank you.
Hi, I'm Bonna, and I started my PhD from this fall, and I am under the supervision of Dr. Aaron Williams, and I'm starting my PhD from this fall semester.
Great, thank you.
Hi, my name is Benga Daniels. I'm a 2nd-year grad student under supervision of Dr. Christie. My research topic is use of machine learning in wastewater treatment and desalination, specifically predicting pollution rejection.
Okay, great, thank you.
My name is Ella, and I'm in my 2nd year of my PhD in environmental engineering, and I'm in Dr. Snow's school. And I'm not really convinced much of my research topic yet. Like, I can't mention the whole thing, but I'm working on water treatment too.
Yeah, great. All right, thank you all. So as we go through the semester, and especially today and this week, if you have a particular interest that you notice, like, oh, my project, really I could use some extra help on this topic, and maybe you don't see that in the syllabus, or you see it there, but it's only a mention, please let me know, and we can adapt a bit to help specifically what you might need. I've so far developed a syllabus just partly copying somebody else, partly looking through the textbook and thinking, okay, maybe it would be good to have probably this number of lectures on that and this number here, to try to follow the course objectives. And I think we have to do that to some extent, but there's some flexibility, and I'm happy to work with you on that as we go. So let's take a look at the syllabus then. I have posted this to our Moodle page. I haven't really developed the Moodle page much, but I do plan to do so, at least have some basic organization. I'll put the slides that we cover there, so you'll get a feel for that, and maybe I'll probably pull that up next class to kind of show you how I'm organizing it. So I expect you to be aware of Moodle and to use it to maybe see assignments or to upload assignments, things like that. But generally, I'll try to give you the instructions in class here. Okay, so we know the class title. Many of you probably know around where my office is. It's right next to Dr. Mo's. It's down the hall from Dr. Bivens and Christy. Info is here for that. If you'd like to meet for office hours, just let me know. I could also add, I'm planning to have office hours for my other class Mondays at 11 a.m. so that I might revise the syllabus and add that here too. But open and happy to meet with you, to talk with you about the course as needed. There's a couple textbooks, one of which, both of which I went ahead and acquired to start building the class. And then just this morning I learned there's one that LSU might already have free on the library system. So I would actually recommend hold off just until Thursday before committing to a particular textbook. I think any of the three that I'm going to end up recommending will probably be good enough to give you the resources for the class. That's my expectation. My plan right now is to kind of follow this one, and I had some trouble when I purchased this one. They never shipped it, and so in a little bit of a not full panic, but like a little bit of urgency, last week I realized I could buy a Kindle version. So part of what I was doing just now was getting Kindle loaded up, and you can download the Kindle app on any device, computers as well as phones and things. And so this is the book then that I'm planning. Oops, sorry. This is the book that I'm planning to be working through. And if I can get to the front, here we go. It's called Aquatic Chemistry Concepts by James Pankow. So that's the first one on our slides here, on our syllabus. So that's this one here. Essentially, that one follows that second recommendation, which is kind of the older, very well known, especially to people who've been in the field a while. And so this is, I think, one of their students, Strum Warner, or Strum Morgan. And so it kind of follows it, modernizes it, and we've got a nice, the Amazon sold me the Kindle version for like $40, just FYI. But I'm also going to take a look at that one that's maybe available on LSU libraries. May turn out that I follow that more so. So still working a little bit, organizing that, but my hope is to give you a good resource and ideally a free resource. Okay, so that's that. I made a mistake in preparing the syllabus. These textbooks are great, but these are water treatment specific, and I had intended to cut those out, so I need to update that. You're welcome to take a look there. They'll have a little bit of water chemistry, but that's not not directly our topic here. Okay, so the objectives, these are kind of what I put on the slide already. We have specific things we kind of need to accomplish with the class. One of which is to deal with these equilibrium problems with computational methods. So one thing that I'm going to have you do is give me some feedback on how comfortable are you, how exposed are you to things like MATLAB, Excel, stuff like that, to try to guide how much time we'll spend developing that. And again, this is not something I've taught, so I haven't developed assignments for these things. So as we go, if you've never touched MATLAB and I ask you to work with MATLAB, we're not going to go so crazy far that that everybody's overwhelmed and doesn't learn anything. That's not what we'll do. Okay. All right. So grading is going to be pretty typical. A couple of exams, and my plan right now is to have a term project that would incorporate whatever computation kind of stuff that we're building over the semester in place of a final. So it might be something like 70% of it is done throughout the semester, kind of maybe alongside the homeworks or something like that, or kind of a part of them. And then I might give you sort of a take-home remaining third of that to finish up, to maybe apply whatever computations that we've built to a particular problem as a kind of that final portion. So that'll be due during finals week. I'll develop those details better and work with you on that. And then probably 3 or 4 homework assignments as well. And so each category there would be equally weighted. Okay, pretty typical expectations here. I don't feel like I need to say too much. Your grad students, you kind of know by now. Communicate with me if there's any problems or challenges, or perhaps if you've got conference travel or something coming up. The nice thing about a small class is that it's a lot easier to be flexible, right? So just be communicative is kind of my expectation there. I do expect you to be here in class for what we're doing, and to participate, to learn here. But I will also mention that I do have kind of a backup resource for you that I've been doing as a way to kind of archive my lectures and things. I'm actually just even right now, see if I can get this over. I'm live streaming for the lecture. And this is going to give us lecture inception here, so we're not going to do that too long. So this will be posted automatically to YouTube. I'll put that link on our Moodle page, so you'll have access to it if you needed. If you did travel for something, you needed to catch up, you could potentially catch it live or watch it later. So I'm going to do my best to keep that going as a resource. Sometimes technology doesn't quite work out, but have a pretty good success rate. So that's something that I plan to do for you as part of how we go here. And you'll see also when I'm taking notes, I'll be writing on the PowerPoint slides. Handwriting suffers a little bit using the tablet, but it's mostly legible. And then you'll have my notes posted as well there. So it should, my hope is that you have plenty of resources from me to learn. And of course, the textbook might be an even better resource, right? It just means you have to read it. Okay. I already mentioned Moodle. We'll use Moodle. And okay. So tentatively, and definitely subject to change here, my plan is to take today, introduce you to the course, talk just a little bit about water as the universal solvent. What are a few things that make it particularly interesting, and really kind of orient our thoughts on the course in terms of, well, what are we really dealing with when we talk about some equilibrium reaction or some, like, the chemistry of something? Like what's happening? And I'll touch on some really advanced concepts, but we're not going to go there in the sense that we need to master these today, the first day of class. That's not my intent, but just to kind of open your eyes to the types of things that are going on in a solution, whether that's gas trying to escape a solution, whether that's water trying to dissolve something, and how do those dynamics work. Just a little taste of that today, and then we'll go into kind of thermodynamics. How can we predict equilibrium chemistry? What are the different ways to do that? A little bit of a refresher on kind of fundamentals of chemistry, activity coefficients, and things like that. So next time it'll be kind of fundamentals and refresher type of class, and then launching into chemical equilibrium. So we'll work on that side of things with a thermodynamics approach to equilibrium, and then we're going to move into solving equilibrium equations rather than from a thermodynamics point, to approach them more of a mass balance and at equilibrium instead of like deriving from the reaction rates themselves. So we'll cover several topics as we go through that, but really build up a baseline understanding of, okay, what are these reactions and what drives them, what's going to change them, why would changing temperature change the equilibrium, that kind of stuff. That leads us into acid-base chemistry. Water is both an acid and a base in some sense, so just dealing with water necessitates that we have some understanding of acid-base chemistry. Of course, then we might add an acid or a base, and then it's all working together there in a more complicated system. So we're going to cover a fair bit of that, talk about the electroneutrality equation, how that helps us understand systems, especially on geochemistry kind of stuff. From there, that's going to be a good place for us to begin working on how do we take an analytical or a computational approach for a problem like calculating the pH of some sample of water if we maybe know what kind of buffers are in there, what kind of minerals are in there, but we don't know the pH, we don't have a pH probe. Could we calculate the pH given some known concentrations of stuff? And if you stop and think about that, from a laboratory's perspective, that's very backwards from sticking a pH probe in there. That's the easy way. But can we calculate that? That's actually an interesting question and worth considering, because we should be able to, but then you start thinking about all the different equilibrium equations that would be involved, and it's like, oh, that's going to be potentially complicated, right? There are ways to get there, and that's where we're going to lean on some computational tools, analytical computational tools. Okay, and that also kind of brings up the topic of the first time we'll touch kind of gas exchange sort of stuff, the chemistry of dissolved carbon dioxide. So the carbonate system will be both an acid and some sort of a buffering agent in aqueous systems that are open to the atmosphere or have CO2 in it. Okay, so that's kind of the first unit I have in mind, and that we could perhaps describe all of that as kind of intro plus acid-base chemistry. We'd have an exam probably on October 15th. If you guys have any issues with that, you'd let me know. If I'm getting close to that time and I realize maybe we need to move that, I'm going to consult with you all to make sure if we change it, that's okay. I'm going to try not to change that for your sake, but certainly with your input, that could change. Then we'd have fall break, and really then get into sort of metals chemistry and different aspects that affect how metals are dissolved in water. So again, thinking of this class as what are the tools that we need to properly perform water treatment. Well, metals are one of the big ones that we want to deal with and relate very much to the different inorganic aqueous chemistry topics. So solubility, of course, we often care a lot about the solubility of metals because if we can precipitate them, that's one way to remove them. So there's and if you notice, that's also an equilibrium reaction. So we're going to be, again, applying it there. Redox chemistry is another part of that. Maybe we don't always think of redox chemistry as an equilibrium, although we probably could to an extent. And then some other factors that might affect their solubility, or what's stabilizing a metal in water. So ligands, things like that. We'd have an exam then before Thanksgiving, have that break, and then cover a couple. So elaborate a little bit at that point on perhaps colloidal chemistry. Something that I do have some research expertise with, colloidal nanoparticle kind of stuff. Even give you a little flavor of that today. But looking through the textbooks, I didn't feel like that was something that I really wanted to have a formal exam topic on, kind of thing. So that's my tentative plan. So the reading for those, there probably are some readings, or I might just simply post some stuff. I'm sure you can find in any of the textbooks. I think there's going to be some segment on that. Okay, then I have the final exam date written there. Like I said earlier, I'm not planning on a formal final exam, but the term project would be due at the end of that class period. As if that, perhaps part of that becomes a take-home exam or something. All right, any questions? It's a new semester. It's been all summer since I've been lecturing, and I have to get used to being the only one talking, just droning on and on and on and on and on. Not my favorite, not my most favorite thing in the world, but we'll try to be at least a little bit entertaining for you here. Okay, I think that's about all that I wanted to show you syllabus-wise. We've got our textbook here. We could take a look. Just real quickly, you'll see that the table of contents really kind of follows pretty well that plan. Today I got some materials from the older book that precedes this one, and so I have a few scans of that to show you. I don't think we're missing anything for not spending too much time in that older book, but if I do find things that seem useful, I'm going to bring them in as best I can. But I do like having an actual digital copy. It makes for nicer copying and pasting than scanning. Okay, so we can see they have this segmented from like a part 1's introduction, then thermodynamics as part of that, so chapters 1 and 2 there. Part 2 is the acid-base chemistry. So the way I have it schemed so far in my mind is the first exam will cover kind of parts 1 and 2 here, where part 1 is mostly review. Probably have a homework on part 1 and then a homework on part 2. And then we would get, when we go into metals, so this will take us through, and we're not going to cover every part of every chapter, that's for sure. There's no way I could do that, or any of us could do that. So for example, and this is a good example, if you find this is something that would be really meaningful for you for research, for titrations in particular, let's say, I'm not planning to cover that in a whole lot of depth, although of course what we're covering is relevant, but I don't think I've assigned any reading there, and I don't think I'm going to draw any lectures directly from chapter 7, for example, but I could certainly change that. Likewise, buffer intensity, those concepts, I'm passing over, but they're there so you know. And then we will touch on chapter 9 here with dissolved CO2, and then move on to part 3. So that's our metal and ligand chemistry, mineral solubility. They have as a completely separate part here, and to me, those two will go into together for one. For the second exam. Okay, so there's several things here. Here's a chapter on the particle size, so that would be our colloidal chemistry. So that's kind of not going to be tested on directly, And I may or may not pull from that section, probably will at least a little bit, but just give you some reference as to why the size, the charge, the nature of a colloid in water, it's not exactly dissolved, but it's close. What is that? How does that matter? What are we dealing with that type of a system where we're between a solid and a dissolved, like a solute? Okay, and we will skip ahead at some point to draw some redox chemistry. That'll help us understand the metal solubility, because if we're changing the oxidation state of a metal, then we're suddenly changing the solubility of that metal potentially. So a lot of times a way to precipitate and remove metals would be to change the oxidation state and then manipulate the chemistry from there so that they'll come out of solution. Okay. Going to, along the way, try to give you some exposure to the PE-pH diagrams and pH versus species concentration, but I'm not sure if we'll fully cover any one of these chapters here. Okay. And like I said before, since I haven't organized and taught this class before, perhaps I'll find that I really wished I would have skipped ahead more or less or something, right? So welcome your feedback and appreciate your patience as we do that. Okay, any questions, concerns, thoughts for me? All right, well, I'll just talk a couple more minutes then about water as the universal solvent. So you've probably heard that before. Water as is the universal solvent. And really it's pretty incredible that water is able to disperse so many things. If we think about some other solvents, you may or may not have used many, but you could think of methanol or toluene or benzene or something. And if you stop and think about what you use them for, of course it feels very different than water. Whenever you would use something like that, it's going to be, you have to probably, in many cases, use a fume hood because it might be volatile. At room temperature, it's probably not good for you. Some things like that. And it's just a different matter entirely. And some things, of course, you're using it because it's going to dissolve that particular thing really well. And it's kind of like, oh yeah, it's a better solvent than water, is kind of the baseline thinking. But then if you were to try to add any salt to it, almost, most of these more apolar solvents, not going to do anything for the salt. And so it's only if you find a solvent that is somewhat polar can you get charged species to dissolve. And so because water is kind of everywhere and we are made up of so much water and all this, we are so used to water as being the normal, but it's actually quite exceptional in how much it does and its capabilities. And it's just very unique. So what is a solvent in general? So there's a couple definitions. Well, one would be an adjective. Your economic assets are solvent, meaning they're easily exchanged. But a solvent as a noun, it's actually kind of related to that same idea. It's easily exchanged, moved, it's liquid. It's capable of dispersing things. And typically we're just meaning that on a molecular level. So it's able to take, for example, a sodium chloride and disperse it as a sodium and a chloride. And have each of those happy instead of having one big crystal structure that sinks to the bottom. So typically a liquid, it's dispersing something or creating a solution, and that's specifically meaning like a chemical or a solution of a liquid. Something that eliminates or attenuates something especially unwanted. Okay, so maybe not truly eliminating, but it might feel that way if you were to dump some chemical in the ocean and you dumped a gallon of it. Well, in the wider ocean, it kind of reaches a point where the concentration near zero. Now, dilution is not the solution to pollution, as the saying goes, right? But in that sense, it's attenuating it if you have enough solvent. to the point where you don't notice it anymore. So that's kind of the definition there. So if we take a look at water molecules, we've got oxygen and hydrogen, obviously. Oxygen is fairly electronegative, and it likes to pull electrons towards it. If we look at the bonding, the hydrogens, of course, are then going to be left a bit positive. And as the oxygen pulls electrons towards it, and the hydrogens are happy to kind of give them away, we get what we call partial charges. So we'll have a partial charge distribution. We can have the symbols usually look like this when we write it. A partial charge associated with these regions, and this water molecule here down in the bottom left, you notice that we're bonding here. Sorry. The bonds will be going here and here, technically, but what's drawn here is the electron clouds. So the electron orbitals that are surrounding the H2O, we can notice that there's sort of this electron dense area, two lobes, kind of opposite of the hydrogen. And this is what will allow our one water molecule to start then interact with another water molecule or some other species, is this in a polar manner. This also makes it a little difficult for them to interact with something that's non-polar, although there's something we can consider there as well. Okay, so that's one of the fundamental features, is that we have water that has both positive and negatives. It's a polar solvent. One side is kind of positive, the other side is kind of negative. And it's pretty happy to work with anything else that has some polarity to it. We have a typical angle between the two hydrogens. It's not 180, right? Because if it was, then you wouldn't really have, it'd be like a little positive on this end, a little positive over here, and then negative in the middle. Instead, they sweep in a bit, and then you have negative in the back and positive in the front, sort of thing. Okay, add to that the fact that you could potentially lose a hydrogen pretty easy, and then you have OH minus as the base and the H plus out there. Or another way to write that, and I think we'll cover this at some point, is you could also potentially add a proton, and then you have H3O plus, which is kind of equal to just H plus in solution, right? It's kind of hard to say which one's which. And so I think at some point the book goes into that, and so maybe we'll dive a little bit into that. But at any rate, what's going on here, there's a lot of things that can go on here to satisfy, to account for charges, and to dissolve species that many solvents could do nothing for. Okay, there's some other reasons why water is a very particular and interesting substance. As far as liquids go, it's quite unusual. So again, thinking about other solvents you might have used, it has quite a high boiling point. So 100 Celsius, a lot higher than most liquids would boil. If you think of ethanol, you know that's going to start boiling a lot sooner. Water ice has a high melting point. If you tried to freeze ethanol, you have to get it very, very cold, right? Which is why you could take a bottle of wine and put it in your freezer, and it's probably not going to burst if it has enough ethanol in it. It depresses the freezing point. And so in that sense, water has perhaps an easier time of sticking together in a structured manner, and a harder time leaving if you heat it, right? So there's something sticky about it that prevents it from leaving and boiling away, but there's something that's allows it to be structured together pretty easily in some sort of ice structure. By the way, there are many different crystal structures for ice, and this may not even be an ice. This might just be a lattice drawn that's might exist in water, like in liquid water. So water ice is very interesting. It's rare that you have, I think, 30 plus different crystal structures that are known to form with water ice. Another very, very interesting and very useful tool or feature of water is that the maximum density that we find for water is actually above the freezing point. And in fact, the water ice is less dense than liquid water. Now, that might just sound a little bit like a weird little fact that's not super relevant until you like accidentally stick a bottle of something that's not alcoholic in your freezer and it busts because it expanded. But if you stop and think about it for a moment, none of the global water cycles in our world would really work very well if water was ice under, like if you pressurized water, if it became ice. The reason for that is as soon as you have an ocean, well, you're pressurizing the water down there. So if that froze the water down there, or if ice sank, that would completely change the nature of any water cycle to the point where we wouldn't have a oceanic cycling. It would probably prevent life from existing altogether in some ways. So it's very interesting and a special thing that water, you can pressurize it and it's relatively incompressible, and that does not cause it to create ice. And in fact, the ice would float if it did. Okay, so very interesting stuff. Has a very high surface tension, in part because all those hydrogen bonds, they're kind of grabby. They're going to grab to one another. They're going to try to stick to one another. So if I were to take a water droplet and put it on some surface for us, that we would see the surface tension, especially if it was a surface that wasn't like trying to suck the water in. In fact, I could probably use my phone. So I recently replaced my phone cover because it was a little bit cracked. And so I've got a pretty nice and clean phone case. See if I can just get a little drop here. And if you see it, I don't know if I can get it so you can see it, but it's a nice domed water droplet, right? And it will probably slide as soon as I drop it, right? And the reason it's nice and domed is because the water is trying to stick to each other, and that they are happy to do that compared to spreading out on what's otherwise a not very polar, a hydrophobic surface. So it's the tension, it's that surface tension that the water is kind of sticking to one another, because they would rather do that than interact with the air or interact with the surface that they're sitting on. So you can actually study the interaction type of a surface based on those three interactions: the water with the surface, the water with the air with the surface, and learn a lot about how hydrophobic or hydrophilic this surface is. Okay. So all that said, water does an excellent job with salts, polar compounds, and I have an example here from some research I participated in as a graduate student, where we had a very apolar molecule called a fullerene. It was just all carbon, like a soccer ball, just a cage. And I'll talk a little more about that in a moment. But so it sounds like it would not do a very good job at that, and it does have a particular challenge with that. It's a very hydrophobic molecule, but I'm putting that as an example here because there's something else interesting that happens, and you can kind of take a look at what it might look like to model a bunch of water around something, right? We would look something like that in a computational model. Here in the middle we see sodium, and we notice that there's plenty of waters that like to come and hang around it, especially with their oxygens kind of exposing their negativity towards that sodium's positive charge. And while it's not formally like a covalent bond or anything like that, it is some type of bonding because it's a electrostatic interaction. There's a partial negative charge associating with that positive charge on the sodium. So bonding in general is not, it's not actually so formal as we tend to think about it. It's actually we might call a chemical bond covalent or ionic or a hydrogen bond, but really these are just essentially scales of how strongly bonded it is. And once we reach some threshold, then we call it a covalent bond. And functionally, that it makes sense. We can understand that there are some bonding situations that are irreversible reactions, but really that's because there's not a good way to pull that back away. You would end up breaking apart some other aspect of the molecule in order to do that, so it's irreversible. So there's a few ways we can estimate that. We could even do it computationally. Thermodynamics is the first topic that we'll deal with that is going to estimate that for us. But we could also use something as simple as the bond length. How far is that distance between the sodium and the surrounding oxygen atoms from the waters? There's probably going to be some vibrations there. Is it weak enough where it can just go away, diffuse away, or is it kind of stuck? Sometimes you'll have some solvent cage that surrounds a molecule or a surface and forms some structure around it. So another part of this fullerene study, here's some fullerenes with water molecules around them. One thing we learned is quite interesting is this all-carbon cage is very, very non-polar. So there's no polarity to it because the electrons in it, there's no hydrogens on this cage. This is just carbon, C60. And if you remember benzene has shape like this, and you've got an electron resonance structure where you draw like that. But really, sometimes you even draw it with a circle in the middle because really the extra electrons are just shared continuously throughout that molecule. And the fullerene is essentially made up of benzene and pentene rings, and you have this shared electronic structure throughout the whole thing. So there's really no point in the fullerene structure that's particularly charged compared to another point. So what does water do? Well, it kind of hates it in the sense that water would really like to have something polar to surround in the conventional manner. But it turns out that the water molecules will actually kind of turn to their side and then grab each other instead. And so what we found is that we end up forming a very tight cage of water that gets even closer to a non-charged, non-polar fullerene than it would some other molecule, because the only way for them to structure themselves around that in a thermodynamically favorable way is to point to one another instead of point to the fullerene. And then they grab each other and it kind of pulls together tight. So it's very interesting because ultimately it's a very hydrophobic substance, but in effect, the water gets really close to it, and very strongly so, because they're pulling so tight to one another. Now, maybe that doesn't really matter too much. Maybe this will still act very hydrophobic in the sense of it's going to much prefer to stick to another fullerene cluster or some other surface, and it's not going to be very soluble in that sense. But it is a very interesting thing to think about, that it's this very, very hydrophobic substance actually pulls the water in very tight. It's a little counterintuitive. It's almost a misnomer. So this is just a few slides, a few images to kind of show, if we were to take a purely computational approach, we could simulate the interaction distance of two molecules. Maybe this is water with a surface or some other molecule, and then take it on over some time. This is a nanosecond computation scale, which is actually a long time for this kind of system, and see how far away from the surface, where this would be like the distance, the bonding distance here, how long are they away? Do they ever come over and then bond, or do they kind of stay far away? We can estimate some things about the bonding characteristics just based on that interaction. So it's kind of a neat thing. And as part of all of that, we might have water clusters, just like we had that water cage that would surround this carbon cage. Or we might have water just kind of floating around in individual molecules. So there's a lot that could go into how water is interacting, how solvents work. There are plenty of tools, simulations that we can use. We're not really going to deal with any one of these concepts at that level in particular, but I hope that kind of gives us an appreciation for what are the interesting things that are happening that make the thermodynamics make some sense, right? How are these molecules interacting, and what's up with water? Why is it special? Why are we going to give it so much attention? All right, I think that's all I've got. Any questions? All right, so next time we'll be into some fundamentals and thermodynamics is the plan. All right, see you on Thursday.